This lesson is on section 8.1, the Pythagorean theorem. This should be a review as the Pythagorean theorem has been taught in many grades coming up till now because it deals with right triangles and it helps you to find the lengths of the sides of the right triangles. But a little bit of history to help us remember. Pythagoras was an ancient Greek mathematician, and he was given the credit for discovering the Pythagorean theorem about the relationship between the three sides of a right triangle. That was about 3,000 years ago. The Plimpton 322 tablet is a large stone tablet that was found in Babylon, well, which is now Iraq. But that also shows the relationship between the three sides of a right triangle. This is a picture of Plimpton 322. It's written in Egyptian hieroglyphs. It's written in Babylonian cuneiform. And the relationship shows how the three sides of a right triangle fit together. What's interesting is that they figure the large stone tablet to be 4,000 years old, which means it was created 1,000 years before Pythagoras supposedly found the relationship, which means that he didn't actually discover it. Moving on to the pieces of a right triangle, there is the hypotenuse, which is the side that sits directly across from the right angle. The one thing that you might remember about the hypotenuse is that it is always the longest side of the right triangle. The other two are called the legs. They can be the same or they don't have to be the same length, but they will always be shorter than the hypotenuse. The actual Pythagorean theorem, a squared plus b squared equals c squared. What that says is that a is a length of a leg, and b is the length of a leg, and c is the length of the hypotenuse. So if you take the length of this leg squared plus the length of this leg squared, that's got to be equal to the length of the hypotenuse squared. The hypotenuse will always be your c value. Pythagorean triples are simply a set of three numbers that fit into the Pythagorean theorem. In other words, they're sides of the right triangle that fit perfectly into the Pythagorean theorem. One such example is 3, 4, and 5. If this side length is 3, this side length is 4, this side length is 5. That's considered a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. Trying to change slides. Sometimes it works better than others. This is frustrating. There we go. Oh, shoot. There we go. Okay, so a couple of example problems. If I give you a triangle in which one of the legs is 4 and one of the legs is 7, can you tell me what the length of the third side would be? To do that, our formula is a squared plus b squared equals c squared. So we would stick 4 in here. We would square these numbers. We would add them together. Now, to get C, to get the length of the hypotenuse, we don't want it squared. So remember that the opposite of squaring something is square rooting it. That cancels the squared, so we get the C alone. And on the other side, we're left with the square root of 65. For our purposes, we will simply put the square root of 65 into our calculator, and we will get approximately 8.1 if we round it to the nearest tenth. The second kind of problem that you're going to see is where I give you the length of one side and I give you the length of the hypotenuse, and you have to back it up to find the length of the other side. You set this kind of problem up a little bit differently than you set this one up. We use the same formula, but you have to make sure that the hypotenuse length goes in for C. So we do 5 squared, and then I just leave the B in there, plus B squared equals 11 squared. And then in this particular case, you'll solve for B instead of C. So it would be 25 plus B squared equals 121. And then we would have to minus the 25 over to the other side. So B squared would equal 96. And then we would take the square root of 96, and we would get 9.8. We'd have to square root and square root. That's how you use the Pythagorean theorem. The biggest trick is making sure that you put the right numbers in the right spots in the formula. The next kind of problem that we're going to look at is if I give you the 3 sides of a triangle and I ask you what kind of triangle it is, we're going to base that on the concept of the Pythagorean theorem. We know that if our numbers fit into a squared plus b squared equals c squared, if our numbers fit into those, then it's a right triangle. But what happens if it doesn't? What happens if those 3 numbers don't fit in perfectly to the Pythagorean theorem? For example, if I give you 3, 6, and 8, I know that 8 is going to have to be my c value because it's going to have to be the biggest. So I'm going to do 3 squared plus 6 squared equals 8 squared. When I do the math, I get 9 plus 36 equals 64, which means I'd get 45 equals 64. I know that that's not true. That means that it does not fit into the Pythagorean theorem, which means the side lengths of 3, 6, and 8 do not give you a right triangle. But just because they don't give you a right triangle doesn't mean that you can't know anything about it. If your triangle is not a right triangle, that means that it's either an acute triangle or an obtuse triangle. It's all based on the fact that that 90-degree angle dictates the length of this side that sits across from it. If it's a perfect right angle, then this 90 degrees fits this side over here perfect. If it's not, for example, when I add these 2 sides, it's too small. The 64 is too big. It's too big for the A and B sides of 3 and 6. Therefore, that means that this right angle had to stretch to accommodate this longer side. Since the right angle had to stretch out to accommodate the side that was too long, that means it's an obtuse triangle. Okay, so if your c squared value is too big for your a and b squared values, then that means it's an obtuse triangle because that right angle had to get bigger. If you would do a problem and it ends up the other way, that the c squared ends up smaller than the a squared plus b squared, then that would be an acute triangle because that means the third side wasn't big enough so that the right angle had to turn around and come in to accommodate that third side. That means that it would then be smaller than 90, so it would be an acute triangle. So if the c squared is too big, it's an obtuse triangle. If your results would end up being something like 45 equals 22, then that means that that c value is too small, and then that would be an acute triangle. The formulas sit like this, that, you know, if a squared plus b squared equals c squared, then it's a right triangle. If a squared plus b squared is bigger than c squared, like this, then it's an acute triangle. And if a squared plus b squared is not bigger than, in other words, it's less than c squared, then it's an obtuse triangle. All right, so you try it now. 4, 5, and 7. What kind of triangle is it? So you would say 4 squared plus 5 squared equals 7 squared. And you would get 16 plus 25 equals 49. 16 plus 25 is 41 equals 49. That means that they are not equal. That automatically cuts out the right triangle. And so it says the c squared is too big for the a and b sides. If c is too big, then that makes it an obtuse triangle. That concludes this lesson. Your homework for section 8.1 is as follows.